both parallel plates and electric potential energy, or electric potential, was the experiment done by Robert Milliken and a colleague, Fletcher, to figure out, this is early 1900s, and they actually could figure out the charge on one electron. And there's the number, and it's itty bitty. And like I say, how could they possibly do that? How would you calculate a number so small? How could you figure out the charge on one electron? And just pause for a moment, and given all the information that these guys had, the stuff now, and this is what they did. Okay. Here's what they did. They set up a parallel plate apparatus, okay, and it was sort of vertical. So I think the positive plate was on the top, the negative on the bottom. They took it's oil drop experiment. They took oil and they sent it through like a little vaporizer, so that a lot of friction was applied to them, so they were all charged. Enough friction that they sort of hypothesized they were stripping electrons, right? And so they had they had positively charged little drops, and they were falling, and then it must be negatively charged drops. They must have added electrons to them, added electrons to them, because they were falling towards the negative plate, but they would stop because they were repelled by the plate below them. And that's the basic idea. So let's look at the picture. So somehow they added electrons to these little drops, right? And they would fall, and they'd try to make it so only one fell at a time, okay? So you have a positive plate, a negative plate, and they'd fall, and they would adjust the voltage across the plates, the potential difference across the plates, like basically adjusting the charge across the plates, just so the drops would stay suspended. In other words, they would be repelled by this plate down here, and the repulsive force would exactly equal the gravity force. Now, at that point, that's not really enough, right? That's not really enough to tell you for sure the charge on them, but it gives you some data, because what they started tracking was the amount of potential that they needed to do that. And they somehow figured out the mass of each droplet, so they could figure out the electric force, the gravity force, which would be equal to the electric force, right? And they would keep track of the potential that they adjusted the plates between. And they got data, tons and tons of data, and they used this formula. They said, okay, electric force must be equal to gravity force, because the drop would be staying still. Well, inside a parallel plate, and you could write this down if you want to on your parallel plate section of your formula sheet, because the electric force would be constant amongst the whole distance between them, it would be equal to the change in electric energy, which is this Q, change in V. This is only true on parallel plates, and so if you're going to put that on your formula sheet, put it underneath the parallel plate section. That leads you to this formula, but then you can say, well, okay, but Fe is equal to mg. And so you isolate Q, and this formula is a great formula you can put down. It's only applicable on parallel plates. Oopsie. It's only applicable on parallel plates, but it is the formula that allowed them to calculate charge, okay? So they know the mass, they know the distance between the plates, and they would know the potential difference between them. And what they did is they looked at pages and pages of data, and they looked for the smallest Q's they could find, right? So they calculated like hundreds and hundreds and hundreds of Q's before computers, right? Not a spreadsheet did this for them. Hundreds and hundreds and hundreds of Q's. And they tried to find the smallest Q's they could find, and they looked for multiples that looked like they were jumping by, and they took the smallest multiple they ever found, and it was 1.6 times 10 to the negative 19. And they said, well, that must be the charge on an electron. That must be the smallest bit. Now, they could have been wrong. It could have been wrong. It could have been that when they were getting that smallest jump, that could have been 2 electrons, or it could have been 6 electrons. And that was the smallest they were able to make a difference of. But lots of experimentation since then has shown that they were correct. Okay, so it was basically, they could have easily been wrong, but they weren't. It turns out, years later, higher precision instrumentation and tons of better methods, and their method back in 1909, fairly crude and basically just making some guesses that they were actually stripping them by 1 electron at a time, and that's it. That's how they did it. And I hope that gives you an idea that something as like on 1909 they were able to figure out a number that small, right? Like very little technology. I mean, these people weren't that much smarter than you, and they could do it, and so could you, right? All these things that seem like they're way beyond us, they're not really. Okay, so let's look at an example problem. We have some sphere, and it's got a charge of minus 3q, whatever that means, but some minus 3 times some number q. We know that it's 1.5 meters away from another sphere, and it has a charge of positive 5q. And then it says the two spheres are brought into contact, which I told you this before. Once they come into contact, they should leave with exactly the same charge, which is kind of like the average of these two, right? And then they're separated by 1.5 meters again. And we know then that the magnitude of the force between them is 0.081 newtons. We want to find the number of electrons transferred and which way they moved, which they must have gone from the negative to the positive, and then find the field and the electric potential midway between them. So it's just saying that originally this was the situation, and then after they touched, they both had the same charge. Now look, y plus 1q, well, it's just like taking the average between the two. You add those two, you get 2q, and then you split it up between them, and they end up with 1. Okay, so they both have a charge of 1q. And again, we don't even know what q is. But we can figure that out after. We just know that they both have a positive charge of 1q. And so we're going to find this q by applying the force formula, because we know Fe, we know R, we know everything we need except for q, right? So you can solve for q and say, okay, so q is 4.5 microcoulombs. That's the charge they have after. Well, what happened here, when we talk about how many were transferred, we say, okay, well, A went from minus 3 to plus 1, so it gave away 4q worth of electrons, right? Charge always, it's always negative charges that move. Maybe you don't remember that, but from previous courses, but it's electrons that move. It's never protons, like unless they're being accelerated specifically. But if you're looking at something giving charge to something else, it's always negative charges moving, right? So in this case, A gave away 4q worth of electrons, and we're saying q is that. So the amount of charge that was transferred would have been 4 times this number. Okay? And then it says, well, that's great. 1.8 times 10 to the negative 5, that was the quantity of charge, and it's saying how many electrons is that? Well, since every electron has this much charge, then you can just say, okay, the number is q divided by the charge on one electron, and there's the number. So you might want to write down this formula, I don't know, the number of electrons is equal to the charge divided by the charge on one electron. You can write it down if you want to, but n equals number of electrons. You might want to put that on your formula sheet if you find that hard to get. Okay, part B in the question is saying right in between, find the potential, electric potential, and find the field strength. So electric potential is just the potential due to A plus the potential due to B, and it's all positives here because we're saying QA and QB are both positive, and you solve and you just get that number. There's an electric potential. 1 coulomb of charge would have 11,000 joules of energy sitting there, potential energy. And field strength is field strength due to A plus the field strength due to B. Well, due to A, if I say that right is positive, due to A it would be positive, and due to B it would be negative because they're both positive charges here, so a positive charge would want to move away from A, but it would want to move away from B as well. And they actually cancel each other out. I mean, here's my things that make you go, huh? How is it possible you could have electric potential, you know, it has potential to move, but feel no force, right? And that's an interesting question. I'll leave you to think about that. How is that a thing? How could that be? So if you can come up with me with a little decent explanation or thought on that, by the way, I'll give you a little bit of a bonus mark. So come talk to me in class about that, and we can have a good discussion, because I think it's a thing that makes you go, huh? How is that a thing? Anyway, I have a couple more examples, but I'm going to put them in another video, so I'm going to stop right now, leaving on my things that make you go, huh? You think about it, and maybe we can talk about it.